In section 6.3, we're going to look at similar polygons, which means we'll look at similar shapes that might be blown up or shrunk down. So what I want you to imagine in this is kind of zooming in and out on a picture. And I'm going to start with a bunch of definitions. So I want you to make sure to copy these down, but make sense of them as well. The first one is that for a figure to be geometrically similar, they have to have the same shape. So a triangle must be similar to a triangle, a square to a square. But it does not necessarily have to be the same size. So again, think of that zooming representation, where I could take a triangle and then zoom in on it, and it will look bigger on the screen even though it's the same shape. So they would be similar. Now, geometrically similar triangles have to have corresponding angles that are congruent. All of the angles must be equal. And the corresponding sides have to be of the same proportion. They have to be of some ratio. So for example, if you take one triangle and you blow it up to 3 times the size, that would be a 3 times ratio. And we call that ratio the scale factor. So we say that a triangle is scaled to 3 times the size. To find the scale factor between two similar shapes, you need to simplify the ratio. So it needs to be the least reduced fraction between any two corresponding sides measurements. All squares are similar. That just makes sense because all squares have congruent sides and 90-degree angles. So one square might have a different side length than another square, but they're going to have the same angles and be of some proportion relating scale factor. And then we can use similar triangles to find measurements of objects that are way too big to measure regularly. So, for example, if I'm standing underneath a building, rather than climbing up the building, I can use similar triangles to compare it to a smaller triangle with the same measurement angle looking up towards the building and estimate how tall that building is. So it becomes very useful. These two figures below are similar, and this is the symbol for similar. It's just a little squiggly mark. Keep in mind, write that down, write similar next to it because I'm going to keep using that. I'm not going to always write similar. Okay, so now that we know that means similar, let's look at the two triangles. Angle F and angle R are congruent. Angle G and angle P are congruent, and angle H is congruent to angle Q. That's by definition of similar because all of the corresponding angles must be congruent, and the lengths of the corresponding sides are proportional. So I look at the sides, and we've got 2 to 3 should be the same as 3 to 4.5, and 4 to 6. So I can write down the angles and the sides that are similar. The congruent angles are the easy to do ones. Angle F and angle R are congruent. Notice I'm putting the congruent sides in between, not the similar signs, because we can say those are congruent. What we can say is similar would be the figures itself. The sides now, we have to write a proportion. So we already said that FG over RP, so what I'm doing here is I'm taking this side divided by this side, their corresponding sides, should be equal to GH divided by PQ, which should also be equal to FH divided by RQ. So let's put some numbers in. FG is 2, RP is 3, so 2/3 should be the same ratio of GH, which is 3 divided by 4.5, which should be the same as 4 divided by 6. When you reduce both of these fractions, so you reduce 3 divided by 4.5 and 4 divided by 6, you do in fact get 2/3. So these are all the same ratio, which means that these two figures are similar. So what I can do is make a similarity statement. I can say that triangle FGH is similar, notice I use the squiggly sign, to triangle RPQ. And it's important that I put the vertices in order, just like we did when we were saying triangle congruency. Do not make the mistake, though, of putting a congruent sign here, because these triangles are not congruent. They're different sizes, but they are similar in their ratio. Using the same picture as before, let's take a look at the perimeter of these triangles. The perimeter is just the outside sides added up. It's the outside area, lengths. So 2 plus 3 plus 4, that should give us the perimeter of this first triangle. 2 plus 3 plus 4, and that is equal to 9. The perimeter of this second triangle, 3 plus 4.5 plus 6, is equal to 13.5. Now, we already looked in the last example between the ratio of the two sides. We had the ratio was 2/3. Let's take a look at the ratio of the perimeters. So we have 9 divided by 13.5. If we simplify this, this is actually equal to 2/3. You can plug it into your calculator, reduce the fraction, and you get 2/3. Notice, these ratios are the same, which means that the ratio of your perimeters should always be the same ratio of the triangles, the scale factor. In this example, we have Emily, who is 5 feet tall, and she's standing from this lamppost, which is 12 feet tall. It's shining down on her, and she's 14 feet from that lamppost. What we need to find is how long her shadow that's created from this light shining down is. So we're looking for this value of x. Now, drawing the picture is very important in this setup. If you don't have a picture, it's going to be very difficult to set up a proportion equation. So I've drawn the picture. Remember, the light's shining down this way. We're looking for x. Now, these are two similar triangles, the smaller triangle and the larger triangle. So what we can do is write a proportion between the two. The height of this leg to the base length here should be the same proportion as the height of the lamppost to this entire base, x plus 14. So what I can set up is 5 divided by x is equal to 12 divided by 14 plus x. I could have written these in the reverse manner if I did x divided by 5 is equal to 14 plus x divided by 12, but there's many ways to approach this. I'm just going to show you one. First thing we do, take the cross product. So we've got 5 times 14 plus x. Notice how I'm using parentheses to make sure that I remember to distribute, is equal to 12x. Now I'm going to distribute. 5 times 14 is 70 plus 5 times x, 5x, is equal to 12x. Subtract a 5x from both sides. Trying to isolate x, we get it to one side, and we get 70 is equal to 7x. Solving for x, we have to divide by 7, and x is equal to 10. So the shadow that this girl is making is 10 feet long. Are these two figures similar? Well, they sure look similar, but we have to do a check. So what we can do is take a ratio. And what I'm going to do is the ratio of 4 divided by 6. Is that equal to the ratio of 6 divided by 9? So what I've just done is I've said one of these sides of the trapezoid, so the leg in this case, is it proportional to this other leg in the second figure? And then is this one up here, the 6GH, proportional to KL? And what we can do is simplify. 4 divided by 6 is the same as 2/3. And 6 divided by 9 is also the same as 2/3, since 6 divided by 3 is 2, and 9 divided by 3 is 3. So check, yes, these are the same proportion. They follow the same scale factor. So we can make a statement, writing the similarity statement. So what I can say is trapezoid GHIJ is similar to trapezoid KLMN. Notice how I made sure that all the vertices matched up. So since G is congruent to K and H is congruent to L, I have GH, KL. They all have to match up to write them in the proper order, just like we did when dealing with triangles. Now it's your turn. Try number 2 in your notes. Pay close attention to the orientation of the figure and what angles are actually congruent. I'm going to temporarily skip number 3. You're going to go back and try that on your own after seeing number 4. You should be fine and be able to do it. I chose to do number 4 because it's a little more difficult. And what we're given here is that these two figures are in fact similar. Pay attention to the way that the vertices are set up. STUV is similar to XYZW, so S and X match up. SX, T and Y match up, they're corresponding. So we need to pay attention to that so that we can set up our proportion. First thing we're asked to do is find the scale factor. So it doesn't matter which way you do this. You can take a smaller figure divided by the larger or vice versa. I'm just going to take ST and XY, and I'm going to set up 21 over 35. Simplifying that, whether it's in your calculator or dividing both of these, I notice they both have a common factor of 7. So I can take 21 divided by 7 and I get 3. And 35 divided by 7 is 5. That's my simplified fraction, so that's my scale factor. Once I have the scale factor, I'm asked to find the perimeter of each polygon. Well, if I take a look at this larger polygon, the one that's a little more blown up, I already have all of the lengths of the sides. So to find the perimeter, 20 plus 20 plus 25 plus 35 gives me a perimeter of 100. Now I want to find the perimeter of this first figure, STUV. I'm just going to call that P. We do not know what P is equal to. You can go through, use this scale factor, and find the length of each side individually and then add them together. But from what we looked at earlier, the scale factor and the ratio of the perimeters should be exactly the same. So what I can set up here is the perimeter of the first figure over the perimeter of the second figure. The ratio of the perimeters should be equal to the scale factor, 3/5. Notice that I know the perimeter of this first figure is going to be smaller than the perimeter of the second, so I did smaller over larger is equal to the smaller over the larger. That's important. Now to go and solve this, take the cross product. 5p is equal to 3 times 100. So 5p is equal to 300. Divide both sides by 5, and our perimeter is 60. And we're done. If you ever go to buy an action figure or maybe a model airplane, it's going to have a ratio on it, and it's going to say it's 20:1 or 1/20th of the regular size, 1/15th, etc., meaning it's 15 times smaller than the actual size. Here we have a replica that's 5 inches tall. So this is my action figure, 5 inches tall. And I know that Hulk Hogan is actually 6 feet 5 inches tall. We want to find the scale factor of the model compared to the actual wrestler. So the scale factor should be a fraction, a small number fraction. First thing we have to do though is 6 feet 5 inches. How many inches is that? Because our numerator of 5 inches needs to be the same as the denominator, 6 feet 5 inches. So what we have here is that 6 feet is equal to 6 times 12 inches, since there's 12 inches in each feet, and that's 72 inches. Now it's 6 feet 5 inches, so we have to add 5 inches, and we get 72 plus 5 is equal to 77 inches tall. So now the ratio we can set up is the action figure is 5 inches compared to the height of actual Hulk Hogan, 77 inches. So now our scale factor is 5/77. If you had written 77/5, you would be wrong because this action figure is smaller. So this ratio needs to be less than 1, 5/77. Mr. Jason and I are standing outside in front of school looking at the flagpole, and we are arguing and curious as to how tall this flagpole is. What we measure is the length of the shadow made by the flagpole. And we find out that the length of this shadow is 264 inches. We also know that Mr. Q, myself, who is standing near the flagpole right underneath it, is 86 inches, and that's the shadow length. So we have 86 inches here, and I really am 74 inches tall. What we need to find is how tall is this flagpole. So I'm going to call that value x. What we have here is two similar triangles. The smaller triangle created by Mr. Q and his shadow's length, and the larger triangle created by the flagpole and its shadow. Setting up the ratio, we can say that 74 divided by x, so the height of Mr. Q over the height of the flagpole should be proportional to the length of Mr. Q's shadow, 86, divided by the length of the flagpole shadow, 264. Notice how this is a little different from what I set up previously. You could have also said, and I'm going to write it over here in the bottom left-hand corner, you could have said that 74 divided by 86, so the height of the smaller triangle divided by the base of the smaller triangle, is equal to the height of the flag, which is x, divided by the base of that larger triangle, 264. Both ways work just fine. Once you have them set up, you have to solve. Take the cross product. 74 times 264 is equal to 86x. So we get 19,536 is equal to 86x. Solving for x, we have to divide both sides by 86. And we get that x is equal to 227, approximately 227 inches. With some change, 227.163 inches. I'm just going to round down to 227. That is the height of the flagpole. Make sure you ask yourself, does this make sense? Yes, it makes sense. The flagpole is taller than Mr. Q, as the drawing suggests, and you can check this by plugging in the ratio if you'd like. If you missed anything in this video, make sure you rewind back, record it down in your notes. I'll be expecting that in class tomorrow, or the next time I see you, rather.